Okay, today I'm going to be we're going to go a little bit deeper into some technical issues, unlike yesterday. And basically, there are two themes. One, there are 2 hours roughly on knock and auto ignition quality and of fuels and pre-ignition, super knock, and all these abnormal combustion phenomena in spark ignition engines. And the last lecture will be on compression ignition engines and fuel effects on compression ignition engines, gasoline compression ignition, which is a very promising area, similar to RCCI, but we'll talk about it later. So in fact, I had another final lecture, which probably is in a handout. Basically, it brings together everything that we said in the last 3 years, but you can see it yourself. I think that we were only allowed 3 hours. So let's start now with fuel anti-knock quality and knock-in spark ignition engine. You can, yeah, it is on, right? Yeah, okay. As you know, knock is caused by auto ignition in the, I see, this is missing here. Somebody's taken the, okay. In the end gas. So there's a spark plug here. It fires, the flame advances, and you have the end gas, which is compressed. Its pressure and temperature goes up with time, and you can have auto ignition there, and that's what causes knock. And knock actually is the name given to the noise that is produced because of the pressure fluctuation. It's like hitting the inside of the cylinder with a hammer, basically, and that's what gets it vibrating, and that's what you here, and that's what you can measure. For instance, if you put accelerometer on an engine, you can measure the vibrations. You can measure on the pressure signal as well. What's happening here? Sorry, something has come on in my right. Yeah, so auto ignition depends on the pressure and temperature history of the end gas, and also very critically on the anti-knock or auto ignition quality of the fuel, which, as I said yesterday, is the most important fuel property for SI engines, not just that, for fuels manufacture as well. I mean, the whole of the refinery is sort of, in a way, built around meeting anti-knock quality. Of course, there are other things as well, but that's a very important property. And this auto ignition process, by the way, is exactly the same as in HCCI engines. It is just in premixed fuel and air mixture, auto ignition happens. In knocking engines, it's only a small part of the charge which goes. In HCCI engines, the whole charge is supposed to auto ignite. And this is one of the reasons, by the way, HCCI engines can't really run at very high load, because if all of this, I mean, remember, a spark ignition engine runs at a stoichiometric mixture. There's a lot of fuel energy in there. And all of it auto-ignited and, release heat at the same time, it would just blow the engine up. And that's the reason HCCI engines have to run at very lean mixtures, and that's why they are limited in terms of the IMEP they can get. Now, so as I said, knock is really the noise that you measure, and this is a typical sort of knocking signal. I mean, if you measure pressure, this is how it would look. For example, I've also shown here, I mean, I'm jumping ahead to the next talk, is a very nasty pressure signal. This is how it would normally look. But sometimes, you can get this kind of event, and that is super knock. And this happens because the flame starts much earlier than you intended to. So what you have to remember is the primary operating principle of spark ignition engines is to avoid knock, because our knock can damage engines, and also, and this is one of the reasons this is the reason it limits efficiency. And knock intensity is measured usually in engine experiments from filter signals, pressure signals, and it's often defined as peak-to-peak amplitude of the filter signal. Actually, all of these, by the way, are subjective measures. They're not truly objective, because the knock intensity that you measure like this depends very much on how your pressure measurement system, I mean, the response, frequency response of a pressure measurement system. And in fact, you can call anything knock. It is completely subjective. Audible knock is usually detected when knock intensity is around, the peak to peak is around 0.2 bar, but this is just a ballpark figure. I mean, if you have keen hearing, you can detect it earlier. If you're hard of hearing, you can't hear it. Okay? So mild knock is a noise problem. It's largely sort of, I say cosmetic. In the sense, it doesn't matter for the engine. But and so knock can also be detected by measuring engine vibrations. Instead of the pressure fluctuations, you can measure engine vibrations. And then this is exactly how modern engines detect knock in order to control, I mean, in order to protect against it. But sustained knock at very high intensities could damage the engine. So in general, in engine experiments, what you do, I mean, this is results from a single engine experiment. And what you find is that for a fixed operating condition, as you start advancing the ignition timing, eventually the engine will start knocking, because auto ignition will happen. I mean, initially it might happen in only one cycle, or then it might happen in several cycles, and the knock intensity will go up. We'll talk about knock intensity in the next lecture. But you can measure an average knock intensity, or average over 300 cycles or something like that. And if you plot it against knock limited, against ignition timing, or ignition advance in this case, is before top dead center. As you advance the ignition, eventually the knock intensity starts going up. And you can define wherever you want as the knock threshold. And in this case, we defined it as, in fact, in this case, 1 volt was 1 bar. So it's about 0.5 bar mean knock intensity. And the spark timing at which you hit your knock threshold is known as the knock limited spark advance. And that is the measure you use to characterize fuel anti-knock quality in engine experiments. The larger the knock limited spark advance, the more advanced you can run the engine on a given fuel, the better the fuel is, the higher the anti-knock quality of the fuel is. So this can be taken as a measure of anti-knock quality in engine experiments. And of course, why is it important? Why is knock? For example, you can see here, in the same experiment, if you plot mean torque against the same ignition timing, you'll see that this red fuel, I mean, you can go up to here, and this is where you hit. We decided this is where it started knocking. And ideally, you would say, we don't want to go beyond that. I mean, so that limits your torque. I mean, and you can do the same thing with efficiency as well. So that limits, so the knock limited torque or the knock limited efficiency is also why you're interested in knock. Because if you go from this fuel to this fuel, you can see you can go up here and you can reach the MBT timing. MBT timing is the spark timing for maximum brake torque, and that's the maximum efficiency point as well. So if you wanted to run this engine at this operating condition, if you ran this fuel, which was 94 RON and 91 MON fuel, you will not reach the full efficiency of the engine. So the engine is said to be knock limited. Whereas this fuel, which is 98 RON and 91 MON, will allow you to reach efficiency. This is why anti-knock quality of the fuel is important. Now, I mean, in fact, as I said, as the ignition timing is advanced, knock intensity increases, and also torque and efficiency increases up to a point. And knock limited spark, I'm just, confirming what I said in the previous two slides. Knock limited spark advances the knock limit, the ignition timing when the knock reaches a preset level, I mean, which you have said yourself it's subjectively defined as the knock limit, okay? And knock limited spark advance increases with the fuel anti-knock quality. Okay? When the engine cannot be run at MBT timing, like that fuel A I showed you, the engine is said to be knock limited. And octane requirement of the engine is the octane index. I'll come to octane index in a minute. Is the anti-knock quality of the fuel, which allows you to run it at MBT time. When knock limited spark advance is equal to MBT timing, the fuel, the octane, the anti-knock quality of the fuel is the octane requirement in the engine. In the previous slide I showed you, you could say that 98 RON is the octane requirement of the RON requirement of the engine, because that's what allowed you to run at MBT timing. I will come to this slide later, but this is, I showed you this yesterday as well. This is very rare in modern engines. In modern engines, this doesn't happen because they have lots of protective control systems which don't allow it to get to this kind of thing. It could happen with superknock, which I will talk about later. Now, how do you define auto-ignition quality of the fuels? Okay, this is a very, very important point, basically. Knock occurs because of auto-ignition, as we said, in the end gas. And what you can do is model the auto-ignition chemistry of a fuel with changing pressure and temperature, which is what a lot of you, I think, have been doing with chemical kinetics. But the problem is real fuels are very, very complex, and we know that we cannot actually build a full kinetic model for that. So chemistry cannot be properly modeled for real fuels. And a most practically important way of studying knock is through the so-called Levengood-Wu integral. You know, the Levengood-Wu integral says if this integral dt is the time, it can be crank angle, which is in fact crank angle in engine experiments. Tau is the ignition delay. If this integral goes to 1, you have knock onset. I mean, that's where auto-ignition occurs, right? How do we, I mean, so if you know tau as a function of crank angle, in other words, if you know tau as a function of temperature and pressure, you can calculate this. But even this is not available for every fuel. I mean, you know, because this data has to be first, you know, measured in the shock tubes or you know, other devices, and the models have to be built, and the models have to be validated against the shock tube data, and then that will allow you to predict this. So this is really not available. So in fact, in the most practical approach is an empirical approach. So fuel anti-knock quality is traditionally measured by research and motor octane number, RON and MON. And both of these scales are based on primary reference fuels, which are mixtures of isooctane and 100. You say isooctane has a RON of 100 as well as a MON of 100, and N-heptane has a RON of 0 and a MON of 0. And the volume fraction of isooctane in this mixture is the octane number. And how do you measure this? You, in the CFR engine, according to the procedure set down by ASTM, which was actually established in 1929, the engine dates from about 1926, you compare your fuel, gasoline, with different primary reference fuels and find out which primary reference fuel actually matches it for knock. I mean, in fact, what you do is you change the, essentially you change the compression ratio. You keep on changing the compression ratio and find where your, you know, test fuel is knocking, and then you try different PRF fuels to see which one matches it. And there are differences, you know, in RON and MON test condition. In fact, the history of this is the first test that was devised was the RON test in 1928, 29, you know, 28 December or something like that. But they realized that the RON test was not predicting what was happening with the fuels at that time and the engines at that time. nearly 90 years ago. So they had to reinvent another method, which is the Mon test. And the main difference between the Ron and Mon test is the intake temperature. Mon test runs at a higher temperature compared to the Ron test. Of course, it also runs at a different speed as well, higher speed, but that is not the most important difference. The most important difference is the intake temperature is higher in the Mon test. So in real engines, what you find actually, the anti-knock quality of practical fuels depends both on fuel composition, which is fuel chemistry, and on engine design and operating conditions, because these decide how the temperature and pressure in the end gas are changing, basically. So, so how should it be defined? You know, so experiments based on like hundreds and thousands of experiments, literally, which were both in HCCI engines as well as spark ignition engines and so on. It is possible to empirically come to this conclusion that the correct way of defining the anti-knock quality of fuels is by the octane index. Octane index is simply a combination of Ron and Mon. And you bring in this value, K value, which is an empirical value. It depends only on the pressure and temperature history of the gas. It has no link to fuel chemistry or anything. So Ron and Mon have some information about the fuel chemistry and the auto-ignition chemistry are two very different operating conditions. As I said, Mon operates at a higher temperature than Ron for a given pressure. And the K value essentially is telling you how far you are from the Ron test condition in your actual experiments, with your actual engine, your operating condition. So K depends only on the pressure and temperature history. And you can see for primary reference fuels, by definition, Ron is equal to Mon, okay? And by this, it's the same, they have the same octane index by this definition, the primary reference. And 90 Ron primary, 90% isooctane and 10% N-heptane will have an octane index of, 90 at all operating conditions, by definition, okay? But the chemistry of real fuels is very different from that of PRR. And octane index depends on K. Why is that? Because for real fuels, if you want to understand it in this term, the Mon is always lower than Ron. The real fuels are sensitive fuels. That means the difference between Ron and Mon is known as sensitivity, S, And because it's not zero, unlike in PRF fuels, which is it's zero by definition, octane index depends on both Ron and K and the sensitivity. Okay, for a given fuel, the sensitivity is fixed, of course, right? So, for example, even take your US regular fuel. Will have 92 Ron and 82 Mon, typically, basically. And what this means is, in the Ron test condition, when K is equal to 0, by definition, like this, it will match a 92 PRF fuel, 92% isooctane and 8% N-heptane. But if in the Mon test condition, if you test the same fuel and compare it to the PRF fuel, it'll knock compared to the PRF fuel. And the PRF fuel that matches is the 82 PRF fuel. Okay, this is already telling you that the anti-knock quality of the fuel depends on the engine operating condition. Of a real fuel. Okay, but the really interesting thing is that in modern engines, K can be negative. In fact, K is negative. I'll explain as we go forward. And this is because, as I said, you remember in the Mon test, for a given pressure, the temperature is higher. But what do you do in what engine designers have always tried to do throughout history is to increase the pressure in the cylinder while keeping the temperature down in order to improve I mean, basically you want to breathe more air in, and everything that you do to improve power density and efficiency in engines, like turbocharging, etc., does the same thing. You increase the pressure for a given temperature, or if you say for a, for a given pressure, the temperature is lower. I mean, in whichever way you want to look at it. So what this means is the engines started, in the 1930s, 20s, started with an average K value of 1, because they behaved like the Mond test. Why was that? Because the engines of that time were very poor in terms of thermal efficiency. They had a compression ratio of only about 6. So they were running very hot for a given temperature. So throughout history, people have been trying to move away from that. Now modern engines are much more efficient, and they have much higher pressure compared to the Mond test for a given temperature. And in fact, we have now moved, so they have been moving away from, on average I'm talking about, K value of 1 towards the Ron test, and since about 1990, most modern engines have moved beyond the Ron test. K is actually negative. So what does this mean? For a given RON, a higher sensitivity fuel, because K is negative, will have a higher octane index. It will behave like, a much higher PRF. So basically, K can be negative if the unburned gas temperature is lower than in the Ron test. But once again, I want to emphasize this: K has no fundamental significance in this. Okay, it only helps to explain the changing behavior of a sensitive fuel at different conditions. I mean, because it helps to bring some kind of order to a lot of very confusing results. Now, let me again explain, depends on, I've been talking about K and the effects of temperature and pressure. See, if you plot the compression temperature in the end gas against pressure, this is the average compression temperature, by the way. As I said, the Mond test is around here. Okay, it's for a given pressure, it says higher temperature. Ron test is around here, and a modern engine could be below the Ron test. And what HCCI engines allowed us to do is really go very far beyond these Ron or Mond tests, because you can't run a spark ignition engine with around here, or especially around there, extremely high. I mean, they'll be extremely inefficient, in fact, if you did that, generally. But it allowed us to, do these experiments at different conditions. And what I did was you define a very simple term. You say the temperature when the pressure is 15 bar in the engine. Well, that means before combustion starts. It's the unburned gas temperature. That allows you to anchor, your this operating point somewhere. So if you say T compression, we call it T compression 15. If the T compression 15 is very high, you can go up and down. You can it describes where you are in this plane, basically. Okay. As I said, modern engines are beyond Ron and have negative K values. And for a given Ron, a lower Mon is better. This is extremely important in practical terms, because this, I'm jumping ahead again, but I want to emphasize this point, and I'll say this again. Most specifications, I mentioned this yesterday also, specifications in the US as well as in Europe assume that Mon actually contributes to Antiknock quality. In the US, Antiknock quality is defined as Ron plus Mon over 2. So it's assumed that they're equally important. Okay? So in fact, what refineries are forced to do is actually try to reduce the sensitivity as well for a given Ron. They want to increase Mon as well, and this has very important practical implications. But the engines are heading in the opposite direction. So there is a real mismatch between where fuels are being forced to, and why is this happen? because these specifications were set around in the US, for example, I think mid to late 50s, where engines were actually there. I mean, that's where the engines were actually. In fact, if you test, I mean, we tested, I remember, an aircraft engine, which was designed in the 50s. And it has a K value of about plus 0.5. Because what, sorry, what happened here? Yeah. What this R plus MO2 means is the K value is plus 0.5. And this was done not just randomly, because that's where the engines were, because engines have moved on now. I mean, they have got, you know, more efficient. So we have moved beyond RON, and this is an important point to remember. So how do we actually measure the K value, etc.? I mean, so what you do is you test many different fuels, okay? And it's important to make sure that there is no correlation between sensitivity and RON. So you have to make fuels up with some primary reference fuels, some fuels which have, you know, all these other things like aromatics, oxygenates, and olefins, and so on. So there is no strong correlation, ideally there should be no correlation between RON and sensitivity, because if there was, you wouldn't be able to pick this difference up. And in fact, this has been one of the problems in the past. People haven't picked it up because these nuances, because the way people used to do experiments is they would have one high octane key fuel, another low octane key fuel, and they used to make intermediate ones by blending them. And that meant there was a, you know, correlation between sensitivity and RON. And then you can't pick this thing up. Anyway, so what you do is we have many, many different fuels like this, you know, of different composition and different RON and MON, you know, and and then you test them in the engine. For example, what you do is, as I told you, in an engine, we measure knock limited spark head bonds as the measure of anti-knock quality. In this case, this was actually, these experiments were done in Toyota, in fact. I mean, they were developing the Toyota, we had a collaboration with them, and the Toyota, I think this engine has been released in 2006 or something like that, 2006. But anyway, what you can do is you can measure for all these different fuels that I showed you, knock limited spark head bonds, and plot it against RON. There is a reasonable correlation, okay? But if you plot it against MON, there's really no correlation. But you can find a combination of RON and MON which gives you an excellent correlation, okay? So in this engine, at this operating condition, the K value was minus 0.4. You know, that's the, you know, that's the but if you ran this engine at a different condition, the K value could be different, by the way. And in fact, you can see for, you know, well, actually, I won't go into this. This is too detailed. I mean, you can read it up in the papers. Let me skip to this. In general, okay, I'll skip this as well. But what, in fact, you find is not just the knock limited spark head bonds. You can do these kinds of experiments with cars, for example, engines in vehicles, because modern cars have this control systems and knock detection systems, which means if they find knock, they will take corrective action, and they will usually retard the ignition. That means their power goes down. And if you're measuring acceleration, and during acceleration, if they go into knock, they will go back from that, and so your acceleration times will go up. For example, in this car, it was a Mercedes A160, we measured power at the wheels on a chassis dynamometer with many different fuels of different RONs and MONs. And if you plot the power against RON, there is some kind of correlation. I mean, there's a reasonable correlation with the R square of 0.84, but there's no correlation with MON. But in this case, the K value was minus 0.454, and that is the best description of the Antiknock quality. So you can measure any property in a spark ignition engine which is knock dependent. I mean, knock limited spark advance in engines, or maximum power in cars. And here is in a Toyota Avensis acceleration times, at a particular acceleration time. Again, you can see as the RON increases here, acceleration times come, or you can say it the other way around, as the RON decreases, because it's taking corrective action, its acceleration times get higher, so it is a bit sluggish. It won't accelerate as well, right? But with MON, there is no correlation. But you can see in this case, the K value was highly negative, for example. So it's almost as if increasing RON by one number is almost the same as decreasing MON by one number in this case. If this value is -1, that's what it would mean. So it really likes sensitive fuels. And what are sensitive fuels? Sensitivity is a measure of fuel which tells you how different it is from primary reference fuels, basically. I mean, that's the main definition. So this engine would, this kind of, in this engine, it hates primary reference fuels. For example, in this case, you can see here, there are many, see this fuel, for example, 9593, okay, has, and compare it this fuel, basically 95 and 85. This fuel is much, much better than this fuel in terms of acceleration time in this case, though it has a much lower MON. And similarly, yeah, I mean, these two fuels. See, this is very much like a PRF fuel, but this one is, similar RON, but much lower MON, and that fuel is much better, for example. So in this case, K is -7. And you can do the same kind of thing in HCCI engines, where if you remember, I told you can go very far away from these RON and MON test conditions, and you get very, very interesting results. For example, in this case, we looked at where heat release occurred, the CA50, which we measure the sort of auto ignition quality of the fuel by measuring where CA50 was. All the tests were done at exactly the same intake temperature and pressure and speed. So the more resistant the fuel is to auto ignition, the later the CA50 essentially. Okay? So when you plot CA50 against RON or MON, there's really no correlation. But with K of minus 1.5, you can get this. So in this case, it is as if K is minus 0.5. But in the same engine, if you ran it in a different way, yes, it is, yeah, okay. No, this is negative K, okay? But you ran it in a different way, where you increase the inlet temperature very significantly. In this case, we are running at low intake pressure, low intake temperature, but very high intake pressure. If you remember those curves, I mean, we were very, very low. I mean, we are well below the RON test condition. But if you run the same engine at a very high intake temperature and I mean atmospheric pressure, I mean for intake, you find that K value is highly positive. It is beyond MON in this case. Okay, so what this means is at this operating condition in the HCCI engine, which is, it really likes PRF type fuels. The low sensitivity is much better. It doesn't like. But in the same engine, if you boosted it and ran it at a lower temperature, it really dislikes primary reference type fuels. So sensitivity is good. Okay? So, I mean, this, again, I'm showing the same type of curve here. I mean, you can see here, these are HCCI type, HCCI results. And you can see, I think if it's beyond MON, it can be plus 2.2. and it can be minus 1.6. These are various sort of knocking as well as HCCI engine results. Basically, you can see there is like a correlation with T compression 15. So in fact, if you plot a lot of data together, the K value against T compression 15, there is some kind of, there's scatter, but there is a very clear correlation. So if T compression 15 is very high, in other words, the temperature is very high for a given pressure, MON test or very highly, with high intake temperature, HCCI test, etc., K value can be very positive. But if you are on the other side, it can be negative. In fact, spark ignition engines are around here somewhere, basically. That's where they would be. And modern spark ignition engines with boosting and downsizing, etc., they're heading, and on direct injection, they're reducing the temperature for a given pressure, so they head in this direction, below. So K is heading to negative values. So why is this so? How can we explain this behavior? Basically, the problem with the octane scale is not because the engine is like 90 years old or something like that. It is that the octane scale is based on paraffinic fuels, which have very different chemistry. Okay? In the MON test conditions, paraffinic fuels are dominated by the negative. Some of you probably know what the negative temperature coefficient NTC chemistry is. Hence, in other words, as you increase temperature, the primary reference fuel, the ignition delay actually, instead of coming down, it increases in certain areas, and that means it becomes more resistant to auto ignition, and therefore it has an advantage in the MON test condition. But because the temperature pressure variations are different in different rating conditions, fuels of different chemistry will be ranked differently in different tests. Right. So, what about octane requirement in cars? If you remember, I said the octane requirement in engines you can define as the octane index of the fuel, which allows you to run at the knock limited spark advance. At MBT timing. In fact, when the MBT timing is the same as the knock limited spark advance, that's the octane requirement of an engine. But in cars, you can do the same thing. You can, I said, see, mean torque against octane index. What you find is that it will increase, and in fact in cars it depends on how they set the car up, how the control system is set up. They might just say we don't want to take any more chances, and we'll just beyond this we won't let it. It won't just keep on increasing. There'll be a limit in the end, basically. So it all depends on how they set it. But you can take this as the octane requirement of this car, basically, at this operating condition. Or you can do so it depends on the calibration strategy. You can do the same thing using acceleration times, for instance. In this car, for example, what you find is it doesn't care if you give it a fuel with octane index greater than 95. Octane index it is, by the way. So it means if you have a 95 RON fuel with 10 sensitivity, that fuel would be more like 101 here. So it is wasted on this engine because the engine calibrators decided this is where they would cut it off, basically. So it all depends on how you do this. So in conclusion, anti-knock quality of the fuel should be defined by the octane index. Okay, and as the octane index increases, performance improves. K depends on engine conditions and it can be negative. And K decreases. I didn't talk about this much earlier, but as octane requirement increases. In other words, the engine is pushed towards knock, I mean, through higher pressures and higher temperature. The more demanding the engine is, usually the more negative the K value is, I mean, generally speaking. So as you, as you try to increase the pressure in the cylinder, this is what happens. The octane requirement goes up and the K decreases. And almost now there are probably a few hundred measurements in a few hundred models, and not few hundred. I was involved in about 50 different cars, show that K is negative in modern engines. And this is profoundly important because, as I said, what kind of fuel should future engines have? I mean, they require higher anti-knock quality, we have agreed, because it helps them to run more efficiently. But what does higher anti-knock quality mean in these engines? For a given RON, lower MON basically is higher anti-knock quality. That's what they like, This is because they will run at lower temperatures for a given pressure, because you are trying to push more mass of air into them, and the source of sensitivity in fuels is everything else but the paraffins, primary, isooctane and N-heptane. Apart from that, you put olefins, aromatics, oxygenates. They all make the fuel more sensitive, and how do we get them? Okay, but this is where the gasoline fuel specifications come in, for example. In Europe and worldwide fuel charters, which I mentioned, there are some things which are probably not quite in line with this requirement. For example, aromatic levels are limited to the 35%. What this means is that it is more difficult to get high RON and high sensitivity, in other words, high anti-knock quality fuels. But this is not going to change in any way. But in some countries, like in the US, MTBE has been banned, for example, which means you take out a very good fuel component, which would have given you high anti-knock quality. Essentially, also from the RON and MON test, fuels are being forced to in a direction opposite to that required by future engines. That is the reality now. Okay, so what do you do? Do you change fuel specifications? And I talked about it yesterday. It is very, very difficult, by the way, and I don't think it's even worth discussing this because it's not likely to happen. But we have suggested another approach where instead of the primary reference fuel, you have a toluene reference fuel. You say toluene is 100, N-heptane is 0, and you give a toluene number rating. And this would be much better because toluene behaves much more like, because it has very high sensitivity. So if for the same RON, you will have similar sensitivity, as the gasoline. And this is an extremely important point. But if you look at this equation here now, what it means is if you have two fuels, one is the gasoline, which is very complex with hundreds of different components in this, and another which is a mixture of toluene and N-heptane, or toluene and isooctane and N-heptane, or a simple surrogate fuel, because I will come to that in the next talk. In that case, if another fuel, surrogate fuel, has the same RON and same MON as your gasoline, it will behave like the gasoline in all operating conditions, whatever the value of K, because those two will have the same octane index, basically, for all practical purposes. In fact, you can test this in many, we have done this in many different engines and engine operating conditions. So when you decide, when you have to say, okay, and many of you are working in chemical kinetics, and one of the issues is always you want to work with a good surrogate for gasoline. So how do you define this surrogate? The best way of defining the surrogate in terms of its response to, or its behavior in terms of knock and all knock limited conditions is to have the same RON and MON as your gasoline, because you know the RON and MON of your gasoline, because you usually, that's how it's specified and you measured it. So you try to make a fuel which has the same RON and MON as the gasoline, and that will be a very good surrogate. You can then do all kinds of modeling on that, and I will come to that. I mean, in fact, I finished a bit earlier today because I skipped a lot of slides. You want to take a break now, or you have questions? I mean, we've got 15 minutes for questions. Yeah. Yeah. No, so in fact, the RON and MON tests are embedded into the industry. They won't go away, okay? But the RON test is the most important one. As you said, I showed you some results where there was a reasonable correlation with RON, not with MON. I mean, but so what you would do in this, essentially, when you have a gasoline, for instance, or unknown fuel, you do exactly the same as in the RON test. I mean, you run it and find out where it is knocking, right? But we have done a lot of experiments with toluene heptane in the RON test, mixtures, and we have a calibration curve. So you find where it's called the digital compression ratio rating, DCR number, in the test. You can plot, the DCR number with toluene number, and you know what the DCR number for your gasoline is. Then you just read off, for instance. Then you say this is 80% toluene and 20% anhydride. That means it's got a toluene number of 80, for example. But then one number is more or less good enough, actually. But it's not. Of course, the point about that with only toluene and heptane is that you're very unlikely to get both RON and MON the same as the gasoline. But if you match the RON, the MON will be almost similar. I mean, it's not exactly the same, but it will be similar. And therefore, the toluene heptane mixture, or the toluene rating, will not be very different at different. You remember when we said with the RON and MON ratings, we said it is 95 RON and 85 MON, for example. The big difference. I mean, they behave like very. Whereas this is much narrower. I mean, in the sense, the gasoline will behave much more like a toluene heptane mixture, because that's how the gasoline is made up of. I mean, that's how it responds to pressure and temperature in terms of kinetics. So, but so basically, we're not saying you should change any test condition, because this has been, people have known that the RON and MON tests are not actually right for probably 80 years, 90 years, But you can't do anything about this, and now there's always, every 10 years, somebody comes, oh, we should have a different rating method. But it won't help as long as you have the same, the scale is based on primary reference fuels, because the primary reference fuels behave very differently in terms of autoignition chemistry compared to real gasolines. And that is the problem, because, in an engine, the fact that this engine is from 90 years ago or something, it doesn't matter, because as I was saying to you yesterday, as far as the end gas is concerned, it doesn't see the metal. What it experiences is pressure and temperature changes with time. And that is so if you provide the same pressure and temperature, you can rank the fuel in, I showed you, for example, some HCCI engines. You can run an HCCI engine exactly at the same pressure, with the same pressure and temperature curve as in the MON test. And you'll find that the fuel ranking will be based on MON. If you run it by changing the intake pressure and intake temperature at the RON test condition, the fuel ranking will be like RON. So you can do it in any engine, but so the test is not important, the scale is important. Well, it is for the future, because one of the things that is happening, of course, now is that you remember, we are pushing further and further from spark ignition engines. You're using things like ethanol much more, you know. And in fact, you're going beyond the raw PRF scale anyway, because the PRF scale, by definition, the highest point is 100, which is isooctane. But as I showed you, in many operating conditions, there are many fuels which behave much better than isooctane. So they have an effective octane, I mean, they have an octane index much higher than isooctane. But if you take toluene heptane, toluene is so far beyond everything, you will be within the scale, you know. So that's another advantage of going to the toluene heptane scale. But I mean, it just, all this thing helps to understand the complexity of, I mean, as I said, the K value, etc., is simply used to systematize all this very confusing sets of data, okay? And I personally don't think the industry will adopt something like that. I mean, they will start, in fact, what is happening, by the way, I mean, this is some, in the US, actually, there is now, when I first published this in 2001, it was for us itself, it was like magic. Why are fuels with lower MON for a given RON better? We just didn't understand it. And it was completely against what the prevailing orthodoxy was at that time. And because you were taught that MON is much more important than RON, and this is how the specification. But in fact, when you test real engines, real cars, you find that some of them really hate MON, I mean, in that sense, you know. So why was this? But now, in fact, all the OEMs in the US now are completely on board. I mean, because they have been testing their own, doing their own tests. As I showed you, we did this test with Toyota, and they did their own tests. And they also find this issue, I mean, you know. And so in the US, for example, there is increasing, I mean, CRC and all have been discussing this, basically, whether we should change how you specify fuels. The least worst thing would be to at least specify fuels only by RON. Okay, so instead of assuming K is equal to plus 0.5 as you do in the US, at least you say K is equal to 0. So you're coming towards modern engines anyway. So and in many countries, for instance, like in Japan and Saudi Arabia also, fuels are specified only by RON. Okay, which means, but some of them, in some places, they're thinking, oh, we should be like the European specification, we should bring in a MON specification, which is exactly the wrong thing to do. And it will have big consequences for refining, for example. Because you are basically, you know, making the less suitable fuels with higher energy, I mean, energy usage in the refinery for modern engines. And this gap will only widen as modern engines become more and more efficient. So there are some learnings from this, which is that RON is much more important. And the US, I think there is increasing at least acceptance, but I don't think it will change very much, because it's a very conservative industry. I mean, basically it won't change. But we need to understand this complexity. But the most important thing from a fundamental point of view is what I said. A good surrogate is the one with the same RON and MON as your test gasoline. I mean, if you are interested in kinetics and things like that. Given that you can't really do the full kinetics for a full-blown gasoline, because it contains too many components. Right? Yeah, let's take a break and come back in 15 minutes.